Hey guys, so I wanted to record a short video just to recap some of the concepts from 5.2 that I highlighted in the class kick from yesterday, but I kind of feel like I did a crappy job because I was not on my A game with the shift to being in the building. Like my head was kind of in other places. So we talked about complement, we talked about mutually exclusive and disjoint, and then we also talked about the concept of the probability of event A or B finding the probability of a union. And we looked at some notation for union and intersection. So I just want to revisit those three things in a short video in case your head was spinning yesterday, kind of like mine was. So we started talking about complements. And so we said that the probability of the complement of A, right, when you have the event A and the superscript C on it, that's the complement of A. If you want to find the probability of the complement of event A, mathematically, that's the same thing as 1 minus the probability of event A occurring. And so I said, well, let's take our Zoom, our Zoom for class, and let's look at the students we have and figure out what's the probability that if I randomly select a student from the Zoom, that their camera will be turned on. So if I let event A be camera on, its complement is essentially the exact opposite, the camera being off. So the complement for A is the camera is off. And if I want to find the probability of the complement of A, one way I can do that is doing 1 minus the probability of the student's camera being turned on. So the way to find the probability of randomly selecting a student whose camera is off, if that's our complement event, I could have simply counted in the participants list to see how many people had their camera off. But another way I could do that would be to count the number of students that had their camera on and do 1 minus the probability that the camera is on. Somebody in F block asked a really good question. So event A and its complement, are they always mutually exclusive? And yes, they are. I actually had to Google that, so I love that question. Event A and its complement, A superscript C, are always mutually exclusive or disjoint, which means that they cannot occur simultaneously. You cannot be a student in my Zoom and have your camera both on and off at the same time. And this is a visual, a Venn diagram of that scenario. You are either here with your camera on or here with your camera off. And notice that those circles don't overlap because those two events are mutually exclusive. They cannot occur simultaneously. It's one or the other. They're complements of each other. Now, I will say the reverse is not necessarily true. So you can have two mutually exclusive events, but they don't necessarily have to be complements of each other. But given an event and its complement, they must be mutually exclusive. All right, so we talked about complement, we talked about these two vocab words, disjoint and mutually exclusive, and then we took a look at the addition, what's it called, the addition rule for unions. All right, so if we want to find the probability of event A or event B occurring, let's talk about this in the context of not camera on or camera off, but something completely different and like a little bit random. So let's say that I let event A be the probability that I could randomly select a student from the Zoom that's wearing a hoodie. All right, so A, student's wearing a hoodie. That's event A. Or B, what's the probability that I'm randomly selecting a student from the Zoom who likes Taylor Swift? Now, there are some people who in the Zoom would be wearing a hoodie, and there are some people in the Zoom who would like Taylor Swift, and there are some people who would actually fit both characteristics. They are both wearing a hoodie and also like Taylor Swift. And now all three of those outcomes, all three of those combinations of characteristics actually fall under this probability, the probability of A or B. This does not mean A only or B only. This means A only, B only, or possibly both A and B occurring. And so I want to talk about this in this context, all right? So you're in my Zoom class. I want to figure out what's the probability that I randomly select a student from the Zoom who is wearing a hoodie or likes Taylor Swift, all right? There are three possible choices here. You could be wearing a hoodie, but not like Taylor Swift. You could be not wearing a hoodie, but like Taylor Swift. And you also, that third option, you could be wearing a hoodie and you also like Taylor Swift. And this is essentially, this is the both piece right here, all right? Both events occurring, A and B at the same time. And that's an outcome that actually falls under this or. This is a union. This is a mathematical notation for or. So the probability of A or B occurring, the probability that I randomly select a student who is wearing a hoodie or likes Taylor Swift. Another way to express that is using that U symbol, that union. And then mathematically, what's happening is this. All right, and this is where I feel like it kind of fell apart a little bit yesterday. This is the probability of A occurring. So the probability that the student was wearing a hoodie, plus the probability that a student likes Taylor Swift, minus the intersection, minus the probability that a student is essentially doing both. That upside down U is an intersection. And it's that subtraction piece I mentioned yesterday where people are kind of like, wait, why are we subtracting it out? So we're going to use this Venn diagram as a visual to understand why that's subtraction. And here's why. And I finally have different color markers so I can show it. All right, so here's the thing. This is the mathematical formula for finding the union of the probability of A or B. Okay, so probability of A. The probability of A, that is this whole circle. This whole circle right there. That's the probability of A. It includes the A-only people as well as the overlap. Probability of B. Now watch what happens here. I am going to shade the entire circle for B, which includes the overlap that I already shaded. So what has happened here? When I add the circle for A and B together, I've unfortunately double counted the overlapping section. I've double counted the intersection. What do I need to do? I need to backtrack and remove one of those intersections, all right? So I essentially need to be subtracting out the overlap one time where people fall into the category of wearing a hoodie and like Taylor Swift. And why? Well, because I already shaded this in red and then shaded again in blue. Another way to think about this is that unions, the probability of A or B, encompasses three separate pieces of this Venn diagram. Okay, so what are those pieces? So think about it this way. Think about if I'm trying to find the probability of A or B, there are three possibilities for who you could be in that combination of events. You could be wearing a hoodie, but not like Taylor Swift. Where do you fall? You fall in this part, this crescent part of circle A. You fall essentially right here. Or you could fall into this category. You're not wearing a hoodie, but you do like Taylor Swift. You would fall in this crescent here. Well, then what's the final combination? You could actually not be A only or B only. You could be both A and B. A and B, the intersection. Wearing a hoodie and liking Taylor Swift, and you would fall here. All three of those pieces together, that is the probability of A or B. So that's another way to think about it. Rather than thinking of adding the probability of A plus the probability of B and then subtracting the overlap, the intersection, you can also think of it as the probability of A only, the probability of B only, plus the probability of both A and B. So I just wanted to make sure I highlighted that in a slightly better version of this video. I'm sorry that this ran a little bit longer than I thought, but thumbs up, team. See you later.